All right, today we're going to dive into one of my favorite algorithms, Union Find. And look, this isn't just for your computer science class. This is actually a really cool story about how a super simple idea can become incredibly powerful with just two little tricks.
So, think about it. You've got a massive social network with billions of users. How in the world do you figure out if, say, you're connected to Kevin Bacon through a crazy chain of friends? Or how does the internet know if two computers can even talk to each other? Well, this is the exact kind of puzzle Union Find was born to solve.
To solve a problem this big, we need a special kind of toolkit. We need a way to group things together, like people or computers, based on their connections. And we need to be able to check, like instantly, which group anything belongs to. So let's build that toolkit.
Now, the main tool we're going to use is called a disjoint set data structure. I know it sounds a little intimidating, but it's really not. All it means is we have a way to keep track of a bunch of items split into different groups, and the key rule is that no item can be in more than one group at the same time. That's it. Simple, right? Okay, so our toolkit really only has three main functions. First, there's make set. This just creates a brand new group with one single thing in it. Then you've got union, which is exactly what it sounds like. It merges two groups together to make one bigger group. And finally, the most important one, find set. This is how we ask, hey, which group does this item belong to? It does this by finding the leader or the main representative of that group. All right, we've got our tools. Let's try to build our first solution. We're going to take the most obvious, straightforward approach we can think of. But as you're about to see, the easy path, well, it can lead to some serious trouble.
Let's start with 6 elements, A, B, C, D, E, and F, each in its own little set. Now we're just going to connect them up in a chain. We'll union A and B. Then we'll union the new group with C. Then that group with D, and so on. We're just linking them up one after another. Seems logical, right? What could go wrong? And here's the result. Yikes. We've created what's called a degenerate tree, which is just a fancy way of saying a long, spindly, and super inefficient line. Now, if we want to find the leader of A, which is all the way at the other end at F, we have to walk up that entire chain. That's 5 steps for just 6 items. Imagine trying to do this with a network of millions. It would be a disaster.
So just how bad is it? In the worst case, this approach is catastrophically slow. We're talking about a time complexity that can grow quadratically, or theta of n squared. To put that in perspective, if you have a million items, that's not a million operations. It's a million times a million, a trillion operations. Your computer would just give up. This simple solution just doesn't work at scale. We need to be smarter. And this is where the magic happens. This is the aha moment. It turns out we can fix this entire mess with 2 brilliantly simple ideas. They're just little rules of thumb, but these 2 tricks will take our slow, clunky algorithm and make it unbelievably fast.
Meet our 2 heroes, union by rank and path compression. With union by rank, the rule is simple. When you merge 2 groups, the shorter one always joins the taller one. This prevents those long, stringy chains and keeps our trees nice and bushy. Then you've got path compression, which is even cooler. Whenever you're looking for the leader of an item, you take every single node you visited along the way and have them point directly to the leader. It's like the tree automatically flattens itself out as you use it. And the code for this isn't complicated at all. Look at the logic for union by rank. We just check which tree is taller. The shorter tree's leader points to the taller tree's leader. That's it. And if they happen to be the same height, no big deal. We just pick one and increase its height by 1. It's so simple, yet so powerful. And the code for path compression is just beautiful in its simplicity. It's this tiny recursive function that does all that heavy lifting. As it's climbing up the tree to find the root, on its way back down, it tells every node, hey, from now on, just report directly to the big boss. So the next time you do a search from one of those nodes, it's a direct shot to the top. The structure literally optimizes itself. Okay, so this is the moment of truth. What happens when we take these 2 new rules and rerun that exact same sequence of operations that created our slow, ugly chain before? Let's see the payoff. And there it is. Just look at the difference. On the left, that's our old, sad, slow chain. On the right, that's what we get with our 2 clever tricks. It's a flat, wide, super efficient structure. Finding the leader of any element is now almost instantaneous. That right there is the power of smart algorithm design. So what happened to that awful n-squared performance? It's gone, obliterated. The new running time is so incredibly fast that for pretty much any practical purpose, it's considered nearly constant time for each operation. We went from impossibly slow to don't even think about it fast. It's a huge win.
So, okay, this is a cool little academic puzzle, right? We made some abstract thingy run really fast. But why should you actually care? Well, because this algorithm isn't just a puzzle. It's a real workhorse that powers some incredibly important stuff in modern computing.
It's the absolute core of algorithms like Crucicles, which figures out the cheapest way to connect a bunch of points. Think designing a fiber optic network. It's used to find out if you've got accidental loops in your computer network. It's even used in scientific computing for things like modeling how water seeps through soil. Basically, anywhere you need to track how things are grouped together on a massive scale, Union Find is probably there, working silently in the background.
And this really brings us to the most important point. Learning about ideas like Union Find isn't just about memorizing code to pass an interview. It's about building up your mental toolkit. It's about training yourself to spot these simple, elegant solutions to what seem like impossibly complex problems. This is the stuff that really separates good programmers from great ones.
So the big takeaway here is that sometimes two small, clever rules can make all the difference in the world, turning a problem from impossible to totally manageable. And it kind of leaves you with a question, doesn't it? What other simple rules like these are out there in computer science, just waiting to unlock huge performance gains? Something to think about. Thanks for watching.